Hi friends, good evening to all. Today we are going to discuss about fault tolerant system. In fault tolerant system, two important concepts. First one is the basic building blocks. Second one is the RAID architecture. We will discuss one by one. We are going for fault tolerant system. We are going to identify the different type of faults. The faults, how it's happening, the faults coming from the failures. So you have to discuss what are the failures happening inside your CAO, inside your system. So types of disk failure we will discuss. So transient failure. The transient failure is nothing but when the disk behaves unpredictable for a short period of time. So when the user accessing the disk particular time or shorter period of time, the disk became unpredictable. You can't get any data, you can't manage the particular disk. Second thing is the bad sector. Bad sector means the page getting corrupted. So when you want to access the particular page, you won't get the page. It becomes the corrupted one. So third one is the controller failure. So controller failure, when the disk controller fails, so when you want to read or write from the disk, you can't do anything. The entire disk becomes the failure. The control of the disk becomes failure. So last one is the disk failure. The entire disk become unreadable and the user want to read any data or read anything from the disk, it become unreadable. So type of disk errors. So you are mainly you are having two type of errors and you are going to perform the fault tolerance. First one is the read error, write error. So what is read error? So read error when you want to get when you want to read something from the disk, you can't read the data or read something from the disk. It's not possible. So again write, when you want to write something, it become failure. So you want to write something to your disk, when you are trying to write, you don't get updated in the disk. So read errors, soft read error, precision read error, unredacted error. You are having three types of error. We'll see one by one. Soft read error, a page is good but read written a bad for short duration. So soft read errors, when you want to access a particular page, it will written the bad. You want to access page A, so it will give some other pages. Persistent read error, the page A is good, but you want written long duration. So when you want to get the particular page A, it will take a long time to load the particular page. So undetected error, a page A is bad but written good. So that is an undetected error. You are not able to detect what kind of error it is. So when you want to read the data from the particular page A, you can get, but returning is good. So that is an undetectable error. So next is coming for write errors. You are having two type of write. So one is a null write, the page become unchanged. So bad write, a page A become bad D. So these are the two type of read write errors. So making a single system stable. So how you are going to make your system become stable? You have to follow some guidelines. So we have to follow some operations. So you have to carefully, you have to read and you have to perform write. The careful read is nothing but a read performed repeatedly until return the status is good. So you are going to read multiple times. So until you are getting the correct repeatable read that you are going to read in the particular disk. Careful write, when you want to write, when you perform write followed by the read until read written the status is good. So this eliminates the null write and the bad write errors that you are doing in the careful write. These two operations cannot be taken care of the decays of events, there is a bad sector, etc. So when you are going to perform careful read and write, you don't support the bad sector. So making a single system stable, you can do it two ways. One is you have to make your read write operation stable. So how you are going to make your read become stable? You have to do the operation very careful by using the paired pages. So paired page is nothing but you are going to write page A. So same pair copy will be written for two different lists, page A, page A. So if the result is bad and it from careful area, read from the other page. So stable write, so perform careful write into each one page, pair the page once after the another. So you are going to perform multiple times the write operation. One after the other page, you keep on writing to the different pages. So what are the issues when you are going to perform this kind of operations? The disk mechanism, single disk failure will happen. So in the single disk failure, we are having the some errors like soft read error, null read error, bad read error, and precision read error. So these are the errors you are having. So however, it cannot handle the events like a disk crash. So when the entire disk get crashed, how you are going to handle? Again, just single disk failure. So your entire disk getting failure, you want to get some data, you want to read the data, you want to write the data. It's not possible when the disk getting crashed. So how you are going to overcome the failure? So you are going, obviously, if I am going to deal with the single data, if any data getting failed, so I can't get the data back. So what are you going to do? You are going to multiple disk system. Same system, you are going to store the data in different disk. So that is multiple system. You are going to do the availability and readability. RAID architecture. So RAID stands for redundant array of inexpensive disk. So it's combines multiple small inexpensive disk drives into a group of yield performance exceeding that one large more expensive drive. Appear to the computer as a single virtual drive. Support fault tolerance by redundant storing information in various ways. So use data stripping to achieve the better performance. So in RAID you are going to use data stripping to achieve the better performance. So RAID stands for redundant array independent disk, system of arranging multiple disks for redundancy. So when you are going to deal with the redundancy, you are going to arranging multiple disks for the same data in redundant. So that is the RAID. So it first introduced in 1987 by Berkeley. So idea has been around since of 1970s. So RAID is now umbrella term for various disk management. So not necessarily for redundant data. So what are the basic issues when you are going to use the RAID? So read small or large, write small or large. So these are two operations you are going to perform on the RAID disk. So access concurrency is a number of simultaneous requests that can be serviced by the disk system. Throughput. So what's the throughput? The performance. How you are going to assess the disk performance? The throughput is a number of bytes that can be read or write from the user based on the user request. So that is simple example, number of bytes read write per second as per the user request. That is calculated by throughput. Data stripping, spreading out the block for each file across multiple disk drives. The strip size is the same as the block size. The strip size is nothing but that what the block is were taken, same for strip size. When you are going to perform the storage anything in your disk, the storage device, so what is the reliability? Based on the reliability you are going to calculate the throughput. The strip will introduce the trade-off between the high input output throughput and access concurrency. Small strip means high throughput but few access concurrency. So large strip size provide the better access concurrency but less throughput for a single request. RAID level 1, you are having the RAID level 0, 1, 2, 3, 4, 5, 6. We will discuss the different levels, what the difference between the each and every level, what's the advantages, disadvantages for each and every levels. So based on the user need, you are going to choose the RAID level. We will see what is RAID level 0. In RAID level 0, no redundancy of data, no fault tolerance. If one drive getting fails, then all the data in the array getting lost. So it's like your CD. In the CD, if anything getting erased, anything getting deleted or something get corrupted, so you can't do anything. You can't get the data back from the CD or DVD. It is high input output performance. Again, it's performing the parallel input output operation. Best storage efficiency. So when you're going for, you want to perform the very storage efficiency in terms of, so how RAID 0 become best storage efficiency. So if I take a simple example of your single CD. So in single CD you won't get any duplication of data. So when you want to access the particular data, the input output performance is good. Again the storage is efficiency because of here you are not using any redundancy of the data. So RAID 0 also known as stripping. The data is stripped across the disk in the array. So in the RAID 0 we are going to use the array concept. In the array how the data getting stored, how we are going to access the elements from the array, then how we are going to read write happening in the array, same operation will be performed in the RAID 0. Each subsequent block is written to the different disk. So we'll see the architecture how it's working for write 0 write operation. So write controller, you are having two empty disk. In the empty disk, you want to store the values. In write 0, the A and B getting written disk in one disk for A, one disk for B. Assume that you are going to write A, B for two different disks. A written for the first disk, there's a disk of A, then it is going for store the next value in the next disk, there is a B. So you can see how it's value getting stored. In the write controller, they keep on producing A, B, C, D, E, F, G, H. Assume that these are the 6 values, the 6 values written given for your write controller. So it will first store the value in A, the parallel value of B will be stored in next disk. Again you are giving a C will be stored in the disk 1, again will store in the disk D. Again write control will produce E will be stored in disk 1, E store in disk 1, F store in disk 2. Again G store in disk 1, H store in disk 2. So this is how we are going to store the values in the write disk and reads. So these are the ways how you are going to store the values and you are going to how you are going to read the values. So same way when you are going to read the values, you have to get the value from the disk 1 A, again you have to get the value from the particular disk B. So here all the A to H values, all the disk values, it's not no redundancy are taken. So if any disk failures happen, so assume that your A getting failed, so you won't get the remaining data. So remaining data remains unreadable or it may be get corrupted. So that is the main drawback of your write controller. If you are going to use write 0, you are going to use A, B, C, D, E, F, G, right? So this is the entire disk you are going to use for your write controller. Without redundancy, you are going to use the disk. How you are going to store in disk 1, disk 2 with the different values. So whenever any disk is getting failure, if A gets fails or C gets fails or D gets fails or D gets fails, so you can't perform the recovery. So recovery is very difficult when you are going to use the write 0. We will discuss what are the problems or disadvantages when you are going to use write 0. The best use of space, every byte of the disk can be accessed in the array. So if any single value even missed in the byte level, it's getting corrupted. So you can't perform the operation read or write in write 0. Very fast read and write. So very quick response when you're going to access read write operation. It's very simple operation, no parity calculation done here. Here you are not doing any parity calculation because whatever value stored in A, you are not taken the redundancy of A. That means no redundancy, so there is no need of parity calculation for write 0. Here no redundancy for write 0, not used for mission critical systems. On disk failure mean it become unrecoverable. So as we have already discussed, if any data getting lost, so like your CD, if any data, even a single data get corrupted in anywhere, entire data become readable. So you can't recover the entire data. Once you get erased, you can't get the data back. So next we'll discuss what is write 1. So write 1 same like write 0. Here we are going to take the cloning. So cloning is nothing but also known as mirroring. So the entire data of A will be taken, again one copy of A that is stored in the disk. So data in what are the data taken that are written to the two disks concurrently. So the first type of write is developed. So it's a simple example how we are using write on writing. What are the values coming? So what are the values are writing here? A, B, C, D. Same copy will be taken for A, B, C, D. Assume that if I writing A value here, same A value you are going to writing here. So that you are doing with the mirror. So assume that you are having A, B, C, D in a particular disk. So same value will be taken for A, B, C, D in the particular disk. So how you are reading the values? So the write control will take the value either from disk 1 A value or disk 2 A value. If any failures happen, you can easily recover because the value of A will available in two places. So if this data getting lost A, so I can replace this value of this A. So this is a mirroring concept. You can easily recovery. Why you are going for RAID 0 to 01, RAID 1. So if any failures happen, you can't recover any data. So here what you are doing in RAID 1, so what are the disk you are having A, B, C, D, you are going to take a clone or mirroring of the all entire disk. So redundancy of data will be taken place here. You are going to take twice the data. So whenever the data getting lost, so you can easily recover from this particular disk. So assume that B getting lost, so I can replace from this disk to B. So this is how you are reading and writing in RAID 1. So RAID 1 recovery, so you can easily recover if any errors happen, you can easily recovery. So any data getting lost, you can replace, then you can add the new disk, you can copy the disk 2, you can replace with the disk 1 that you are doing with the RAID 1. So let's discuss the RAID 1 pros. So it's a good redundancy, 2 copies for every block. So what are the data I'm going to have? We are having 2 copies of data. Even when one copy getting failed, so you can easily get it from the other copy. So past read, so can read the 2 blocks at the same time, more disk. So time will be taken based on the disk size. So writes are upsettable, no intense correlation on rebuild, just a copy. So you are not doing any rebuild correlation, you are just to take a clone or mirroring of the particular disk. Here the problem, the space. So using a 2, if you are going to use a 2 disk, you have to use the half of the space. If you are going to use a 3, you have to use 1/3 of the disk. So simple, if you are going to use 1 disk, you have to take a copy of 1 more disk. So number of disk you are going to use, again you have to double the number of double the disk you are going to use. So writes are not faster as per the write types, so very expensive. So your space keep on increasing. So whenever I am going to take the multiple disk, the expensive will become high. So it's become very expensive. So disk mirroring, right when you are doing the disk mirroring. So disk mirroring nothing but the entire disk will be taken as a mirror. So you can take you can see in the diagram. So A, B, C, D are taken. So disk mirroring, what a disk is available, you are going to take the entire disk become the mirror. So I am taking a clone of A, B, C, D, again A, B, C, D. So like that, what a disk is coming, you are going to take the entire clone of the particular disk. So your best read performance may be double. 2 write performance, 2 disk to be written. So here you can read it easily, but when you are going to write anything, so whatever things you are going to write A, again you are going to whatever thing you are writing, it will get updated in the A. So it becomes the poor write performance, good fault tolerance. So when one pair getting failed, so assume that this A, B, C, D getting failed, so you can easily replace with the A, B, C, D. So it become good fault tolerance. Next topic we'll discuss RAID 2. In RAID 2 you are using bit level stripping. In bit level stripping you are using humming code, a form of error correction code. You are going to using a humming code, whenever the errors happen, you can overcome the problem by applying the ECC. So here you are going to use and tolerate disk 1 failure. So redundant disk you are going to use order of log total disk. So this is a formula when you are going to use the fault tolerant disk on failure. So you can call it the number of redundant disks. So assume that you are having multiple disks. I am having 1000 disks. In the 1000 disks, so how many redundant disks you are having? You can get the 1000 disk of 1 failure. So out of 1000 disks, 1 disk getting failure. So what the tolerant disk 1 of 1 failure. So you can find out from the formula. Here better storage efficiency than mirroring. When you compare to RAID 1, it become more efficiency. High throughput but no access concurrency, expensive write. So example you can discuss for 4 disks, 3 redundant disks to tolerate 1 disk failure. When 4 disks are going to use, 1 disk getting failure, we are having 3 redundant disks to overcome the failure. So RAID 3, we are using a byte level stripping with parity. So compared to RAID 2, what's the difference between RAID 2 and RAID 3? In RAID 2, we are using only byte level stripping, no parity. So in RAID 3, we are going to use the parity. So what is parity? So parity is nothing but you are going to use the value of A1, A2, A3, A4. So all the value of chip 0, chip 1, chip 2, chip 3 will be taken. That is A0, A1, A2, A3. The value of all the way will be stored in the A parity. That is value of 0, 1, 2, 3 will be stored in the disk of A. If any failures happen, so no need to access B, C or D. If any failures happen in A1, right, A0, A1, A2, A3, so no need to go for B or C or D 0 to 3. So what I can do, I can go with the A2, A3 with the parity of A. So that you are doing with the parity check. Here no need to perform ECC, it is your error checksum. So since a controller know which disk is an error. So previously in RAID 2, I had to go for A0, A1, A2, A3. So out of this 12 disk, so where is the problem is happened. So which disk getting failure. So I have to call it. So I have to spend lot of time. Which disk is having a failure. Assume that if I am having 1000 disks, out of 1000 disks, which disk getting failure, I have to find out. Then I have to replace the particular disk. So in this RAID 3, the controller will find where is the problem is happen, which disk is having a error. From that easily can find out, and the RAID 3 will solve the problem. So the parity is enough to tolerate one disk failure. So how we are going to easily find out the particular problem? So based on the parity. So in RAID 3, best throughput but no concurrency. One redundant disk is needed. So I am having multiple disks. So only one redundant disk is needed. So here become compared to RAID 2, it become less expensive. RAID 4 it's a block level stripping. Chip size introduces the trade-off between the access concurrency versus throughput. So what is throughput? If I taken the strip size, in the strip size how many bytes of data you are going to read and write per second as per the user need or user request. You are going to call it block interlude parity. You are going to call it in the RAID 4. Parity check you are going to perform with bottleneck. So you are going to identify when you are going to perform multiple writes at the same time. So I am having 1000 disks. In the 1000 disks, I am going to perform multiple writes. It's maybe a small write or large write. So I am going to perform multiple writes with the multiple disks. So what I have to call it the parity disk. So why I am going to call it parity disk? So previous example I discussed A, B, C, D, right? So out of A, B, C, D, which drive I am going to write. So whether I am going to update only A or B or C or D. Again A, whether I am going to update in 0 block or what first block, second block, third block, fourth block. So I am going to call it based on that bottleneck will be removed. So bottleneck is nothing but when I am going to perform multiple write, so the system get confused where I am going to show the data. So the error may be happen. So how we are going to overcome the problem? By using the RAID 4. That is, you are going to with the multiple at the same time, you are going to remove the bottleneck. No problem for small or large reads. So if you are going to perform multiple disks, you are having the problem. When you are going for small or large reads, no problem when you are going to perform the write operation. Whether it's a write read, the read may be small or large file size, there is no problem when you are going to perform the read operation. In general, writes are very expensive. So read, modify, write. For small write, you have to read all the disk, modify the parity, and then only write back along with the new data. So when you are going to perform any modification on the data, you have to first read the data, then you have to read what's the parity check, then you have to write it, then only you can perform the any new data updation for the particular disk. So read, modify, write is well obvious in large rate. So these are the how its RAID 4 is working. So RAID 5 block level stripping with distributed parity. The parity is uniformly distributed across the disk. So the parity generated by using a AND gate, OR gate, you are going to use some logical gates. You are running the different blocks A to E. You are running the parity. So parity are going to generate. So you are having the A2, A3, so fourth you are having the parity, again you are having the B2, B3 you are having the parity, C2, C4 with the parity, D2, D4 with parity, again E2, E4, the parity. So all the A to E, all the five different blocks, then the parity will be generated for red block by using this particular circuit. This may be a AND or OR circuit. So parity is uniformly distributed across the disk. So in this case, the parity will be generated for all the disk A to E. The parity will be given uniform for all the disk. So what are the update you are going to perform, right? So if I am going to give A2, so automatically the parity will be known for all the blocks, particular out of this A2, E5. So any problem with A1 or A2, the particular block get updated because the parity is uniformly distributed. So it reduces the parity of bottleneck. It reduces the parity of bottleneck. So best and small large read same as RAID 4. So best to large RAID still costly for small RAID. So when you're going to perform small RAID, because it's become very expensive. So problem inherent in all RAIDs, correlator failures, identical disk produced from the same assembly line and they execute the same amount of time tend to fail together. RAID atomicity. What happens when there is a system crash between a block being written and it associated with the parity block? So it becomes the atomicity. RAID does not protect from bad data, overwriting or good data. So let us take example of virus or user error. It don't support. You have to take your own risk. RAID solve the problem of uptime, availability, and not data integrity. Applications, different RAID used for different purpose. If you are taken RAID 0, it is used in photo scratch disk, video editing workstation. You are using the RAID 0. So these are the application areas where you are using your RAID 0. You have taken RAID 1 plus 0, so all your database server. You have taken your all the database server, SQL server. You are using the RAID 1 plus 0. So RAID 5 and 6 is like a file server. So when are you using your FTP? File transit protocol, you are using your RAID 5 and 6. Web server with static content. Web server with static content supporting RAID 5 and 6. So web server with the data becomes static. So we are going for dynamic, you won't use RAID 5 and 6. So these are the basic principles how your RAID architecture is working 0 to 6 levels.